Good morning, children. I hope today the light and all the other the parameters will be in favor and we can have a continuous class without any disturbances. Okay. So now that I can see that many of you have already joined, let us begin our class. So today we are actually going to have a very small class because as I was telling you all that our topic of statistical mechanics is almost about to finish. So what are the points that we will be learning today? Today actually we are going to see how Fermi Dirac statistics is applied. Okay, where are we going to apply them and how do we use that Fermi Dirac laws that we have already discussed. Now under those points we will see the how does the Fermi distribution look like. When I say Fermi distribution, basically it is how the particles or the occupancy looks like at temperature 0 Kelvin, which is absolute 0, and also when it is greater than 0, which means at normal temperatures. Okay, this is the first thing that we will learn today. And then we will also apply this Fermi Dirac statistics to one of the systems which I have been discussing lately called the free electron gas. So we will see how we can apply this Fermi Dirac theory considering that electrons are fermions, and we can apply that over the system of free electrons in a metal. So these are two small points, that is our learning objectives today. Okay, so let us begin. Now, before I really go into the topic, let us just take a small recap of what we have already done. What are the things we have already done under statistical mechanics? We have seen that there are basically three categories of statistical mechanics, and anything and everything in this universe belongs or follows either of these three statistics. We have called them as Maxwell-Boltzmann statistics, Bose-Einstein statistics, and finally the Fermi-Dirac statistics. We have compared or we have seen that how one statistics is different from the other, right? Rupam is telling the microphone is not catching. Is my voice audible? Please let me have some feedback. Is my voice audible? Because without the voice, the entire class will have no meaning. Okay, okay, nice. So where was I? We were talking about the three different statistical mechanics classification, right? Now, under them, once we were trying to compare each of them, depending on say their spin, the wave function, their property of following Pauli exclusion principle and all, we have seen that each of them is different from the other. Correct? Now, in this scenario, the very important, the last point that we had discussed was called the distribution function, which means how these particles, say a boson or a fermion, distributes itself over various energy levels provided with various degeneracies. Now, those distribution functions, if I may call them, actually are the law according to which these particles will be distributing themselves. So this is very, very important. Now see what we have already done. We have seen how the individual distribution function for these three look like. Today let us see that how we are able to apply this distribution function so that we get to know more about these systems. I will only be telling you about the Fermi Dirac, about the application of FD statistics today. Basically, there is a very little part of application of Bose-Einstein in your syllabus, which I guess can be done very easily with the help of a note, which I will be providing later on. In case it is required, we can always discuss in our group. However, these 2 points are very, very important, which falls under the Fermi Dirac, and hence it is good that we study it today. Fine. So let us begin with our first point, which is the Fermi distribution curve at absolute 0 and at greater than absolute 0. So let us begin. Now, since we are doing this for the Fermi Dirac statistics, which distribution function will I use? Obviously, I will use the Fermi Dirac distribution function, isn't it? And when I am doing this for the Fermi Dirac distribution, I will be applying this basic thing for the fermions, right? Now, reminding all of you, how did we write the distribution function for fermions? We had written this as Ni by Gi is equal to 1 by e to the power alpha plus beta Ei plus 1, and reminding all of you, what was this alpha? This alpha was minus Ef by kT and beta was 1 by kT. We had defined this term Ef as the Fermi level. Fermi level is the particular energy level which is occupied, the highest occupied energy level occupied at temperature T is equal to 0 Kelvin is the so-called Fermi level Ef that we have written over here. Now what I would like to do is, this was the general formula where I had written it in terms of an alpha and a beta. What I would now like to do is to put in these values so that this distribution function is exclusively written for the Fermi Dirac. Then what will I do? I will take this and put it over here, and I'll also put the value of beta as 1 by kT. Then how will this look like? This will then look like, since Ei, this is a positive quantity, whereas alpha is coming with a minus Ef, can I not write it like Ei minus Ef by kT plus 1? See, all I have done is I have put in the values of alpha and beta from our formula, and this is how the distribution function of Fermi Dirac statistic looks like. Fine. Ei is in general, any arbitrary ith energy level, and Ef over here is the Fermi energy level. So this is the distribution function of a Fermi Dirac system. Now what are we going to see? That how this particular function, how this is going to take up values when the system reaches, say, 0 degrees Celsius, 0 Kelvin, or at higher temperatures from absolute 0, which is greater than 0 K. Alright. So, let me just take up some more values, place over here. What I will do is, I am going to now plot the value. We will find out the values. Just excuse me. Don't. I'm so sorry. There was little bit disturbance in the video, I guess. It was moving. So, what we are going to plot, in our x-axis, we will have energy, and in the y-axis, we will have the distribution function Ni by Gi. Now, sometimes Ni by Gi is also called the Fi. Okay, because distribution function for the ith level. So, along the y-axis, we are going to plot the Fi. But now let us find out how this is going to vary when we take the system from one value of temperature to the other, when we change the value of energy from one value to the other. Fine. Now let us write down the distribution function once again. I would also like that you also please write with me so that it becomes like a practice for all of us. Fine. So distribution function, as we have already written, is e to the power Ei minus Ef by kT plus 1. Right? Now my first condition. Now let this condition be temperature T is equal to 0 Kelvin. So the first condition that we are looking into is a situation when the temperature is 0 Kelvin. Fine. Which means this T over here, we are going to put it as 0, which means we have taken the system to an absolute 0 level. Fine. In this scenario, there can be two conditions. Under this 0 Kelvin temperature, we can have two cases. And what is that? This value of Ei is less than the value of Fermi level, right? So the first case may be when Ei is less than Ef. Are you following me? What we are doing? We have taken the temperature value to be 0 Kelvin, And we are thinking about the situation when the energy that we are talking or we are considering is less than the Fermi level. So somewhere along our energy axis, suppose if this is the value of EF, now we are considering the values which are less than EF, which are less than the EF value. So how will this distribution function or this distribution turn out to be when I put in the value of T as 0 and I put in the value of EI less than EF? Now let us put it over here. So what will I do? Obviously when I put T is equal to 0 over here, this is going to be an infinite e to the power infinity. However, please remember, if EI is less than EF, if EI is less than EF, this quantity in the numerator is a negative number, isn't it? So it is as if a e to the power minus infinity coming out. Are you all with me? What I have done, I have put in the value of t is equal to 0 and I am considering EI is less than EF. Under this situation, my numerator of e to the power EI minus EF is a negative value. And in the denominator, since t is equal to 0, the entire quantity is a e to the power minus infinity. Right? Now, if I have when I ask you the value of e to the power minus infinity, what is e to the power minus infinity? Which means e to the power infinity, 1 by e to the power infinity. And e to the power infinity is infinity, which means this value is 0. This value 1 by infinity is obviously going to be taking the value 0. So what we are left with in this situation is a 0 from the first term, right? So what do I have now? What am I left with? 1 by 0 plus 1, which is 1, which means this will be having the value of 1. Are you all with me? So when I am under these conditions of 0 Kelvin and EI less than EF, how will I plot this graph? Suppose this value is obviously 0 and somewhere this is the value 1 for Fi. For all the values of energy less than EF, can I not plot it as a 1? Because for all these values, the distribution function takes up the value 1. Right? So I hope all of you have understood how we got this. We were working, I will repeat it once again so that there is no confusion. We were working with e to the power EI minus EF by KT plus 1. Now EI minus EF is a negative value because my EI is less than EF, plus this t is 0. So this component, this entire power of the exponential is a minus infinity for us. And e to the power minus infinity is nothing but 0. Correct? So in this scenario, we are left with a 1 by 1 or distribution function Fi getting the value 1. And when we have seen that for any energy value which is less than EF, this Fi value will be taking the value of 1. So from here till the EF value, till the Fermi level energy, we can plot this as a straight line with value 1. Very nice. So this was one of our conditions. Under the same Kelvin, temperature is equal to 0 Kelvin. Now we can take up a second case. And what is that? The case is now that EI is greater than EF, which means for the values of energy which are now along this positive side after our EF. So how will our distribution function now look like? Again, going back to our formula, e to the power EI minus EF by KT plus 1. Once again, now see, T is equal to 0, but now EI is greater than EF. So this power is a positive infinity, e to the power infinity. Right? Now, obviously, you all will be agreeing with me when I say that e to the power infinity plus 1. E to the power infinity is infinity. And infinity plus 1 is obviously again infinite. And what is the value of 1 by infinity? It comes out to be 0, correct? So it comes out to be 0. So in this scenario, the distribution function is taking up the value 0. So what is the physical significance? When the energy levels, when we are considering the energy levels above Fermi level, they are not having any occupancy. Ni by Gi is coming out to be 0. So if I had to plot this, how will I plot? Over here, this entire thing would be in the 0 level. Or if I may use some other color so that it is easier for you to understand. When I was drawing this for energy levels till EF, we had 1, and now when I am plotting it for 0 onwards, this EF onwards, it is this. So as if I was to draw a continuous graph from this value to the EF, this value was taking up a 1 value. Suddenly it drops to 1 and then suddenly it drops to 0 and then continues with the value of 0. So is this now understood by all of us? This is how the curve or the plot of distribution function varies when we change the energy as well as the temperature. Fine. Now this particular example is only for temperature is equal to 0. Fine. So everybody has understood up to now? Nice. Very nice. So we have seen one case when the temperature was 0 with two subcases, EI less than EF, EI greater than EF. Now see, yesterday I was telling you, remember that how we define Fermi level? We define Fermi level by the highest occupied Fermi level at 0 Kelvin. Now see, that result is again being corroborated over here. We are getting the same result back again, which means that temperature is equal to 0. All the states which are having higher, which are above EF, do not have any occupancy. Their occupancy, their distribution is 0. Right? Yes. Kajal is asking, ma'am, what if EI? Now, at EI is equal to EF, exactly at EI equal to EF also, it is remaining in the 1 range. It is in the 1 range. Okay, that is the highest level. That is the highest level which is occupied. Above that, everything comes out to be 0. The distribution comes out to be 0. Fine. Now our second case has to be talked about. What is the second case? The second case is the case when this temperature is no longer at absolute 0. It is greater than 0 Kelvin. What will happen? When I really take the system from an absolute 0 to any temperature above 0 Kelvin, this is what again needs to be talked about. Okay. Now what is it? Okay, what is Kajal? Yes, Kajal. It becomes 0 by 0. So that exponential term is 0. So what are we left with? 1 by 0 plus 1. So 1 by 0 plus 1 is 1 by 1, which means the value is 1. Right, Kajal? The exponential term in E is equal to EI. EI is equal to EF is also giving me that exponential term is coming out to be 0. So 1 by 0 plus 1, which means 1 by 1, which is 1. So over there also, this particular value can be written as 1. Okay? Yeah. So now we are considering the situation when the temperature is greater than 0 Kelvin. So what will happen? Now let us see. Again, if I write what is the value of EI, 1 by e to the power EI minus EF by kT plus 1. This is what we are left with. Now, in this scenario, when I am putting this t which is not equal to 0, we are not having any infinite like situation, right? Then what happens? I will first begin with a situation where under this EI is equal to EF. Temperature is now no longer equal to 0. However, now we are considering the situation that the energy level EI is equal to EF. Then what will I have over here? Please see. EI is equal to EF. which means T is finite, it is not equal to 0. So e to the power 0, we are going to get an e to the power 0 here, right? So did you all follow what I said? We are now considering a situation temperature greater than 0, but energy value EI equal to the Fermi level EF. Under this situation, EI minus EF is same. So EI minus EF will be 0. So e to the power 0. And what is e to the power 0? E to the power 0 is 1. So under this condition, I have 1 by 1 plus 1, which means 1 by 2. So see, this distribution function at temperatures higher than 0 Kelvin and at the particular Fermi level, what is its value? Its value is somewhere exactly at half. So if I may point that point over there, it is this point. It is at EI is equal to EF and the value is half. Now since this is only a single energy value, EI is equal to EF, I have only plotted it like a point. I have not made it like a continuous changing graph because this is only one point. Fine. Now what happens? Now when we, let me again go back and write down the formula. E to the power EI minus EF by KT plus 1. Now when we are considering the situation for EI less than EF with T greater than 0, you know how the plot will look like? The plot, I am not, because that is continuously changing and that is a finite value. I am not going to, I cannot actually show you how individually all the values will change. I will just show you how the graph looks like. In this case, the graph looks like this. And when I take the values of EI greater than EF, it looks like this. So this graph at 0 Kelvin is just like a step function. Either has a value of 1 or a value of 0. However, at greater temperatures, it varies like a slowly changing graph. Okay. And exactly at the value EI is equal to EF, it takes up a value of half. Right? Yes. Very good. You all have already found out the values and you are telling the correct answer that it is half at EI is equal to EF. Now, one more thing should be noted that suppose this temperature, as we have already said, that this temperature T is greater than 0 Kelvin. But how, suppose now this temperature I increase further. Say if this was temperature T1 and I now want to look at the curve for T is equal to T2, where T2 is greater than T1, how will it look like? This graph will become more and more flat. Okay. So, let me just write this to you. This graph, this one which I have drawn is for another temperature, but this one is less. This T1 is less than T2. So as I am going to increase the temperature, this variation will be becoming more and more flatter. And as I am going near to 0 Kelvin, what will happen? This will become more and more steep, and finally at T is equal to 0, it will exactly become the step function 0 or 1. So is this understood? So please note this particular fact that this is how the fermions react. This is how the fermions actually distribute themselves in their various energy levels at T is equal to 0 or at T higher than 0. Okay. So this was about our first point, that how the fermions will be distributing themselves, or what is the Fermi distribution law for Fermi systems, right? Now, if this is understood, now let us move forward to the second level, which means we are now going to apply the same Fermi Dirac statistics to a particular system. Over here, when we were discussing, this was applicable for each and every Fermi Dirac system. But now what we will study? Now we will study about a system, about a particular system which is falling under the Fermi Dirac statistics, or which constitutes fermions. Right? Now Arjun, We are talking about the temperature absolute zero. Now, once again, think what is the question you have asked. Is there any possibility that there is a temperature, absolute temperature going T less than zero? Is it possible? Not expected from you, Arjun. All right. So now all the temperatures that we have written here was not in degrees Celsius, was not in Fahrenheit, it was in absolute zero, Kelvin. And there is no possibility, there is no, I mean, we can never have T less than zero. Impossible. Okay. Yeah. So now let us move forward with a real life system where we have fermions. And actually, what is that particular system? That particular system is called the free electron gas. Now, I think lately I have been telling you about the free electron gas once or twice I have talked about it. But let me explain that to you once again. What do I mean by a free electron gas? Now see, suppose we are considering a metal. Metals are good conductors. But what makes them good conductors? If you remember that in metals, there are large number of free electrons. Free electrons means the electrons which are not tightly bound to the individual atom of the metal. But suppose this is a bar of metal, this is a bar of metal. Inside this, there are Avogadro number of atoms. But from those atoms, it is likely that large number of atoms electrons have come out of those atoms. They are not tightly bound with those atoms, but they are within this structure. So what is happening to them? They are now randomly moving around within the matter at their own will. And this motion of electrons, this is considered to be they behave just like the atoms of gas. Okay, so we call these electrons now as the free electron gas. See, their behavior is random and their behavior is just like gaseous molecules or atoms. But now they are not atoms, they are electrons. So they are fermions, and we call these free electrons in the matter as the free electron gas. So now if I want to know what is the behavior, how they are going to distribute themselves as per the Fermi Dirac statistics, we can always do so, because these electrons are after all fermions. They have spin half. They follow Pauli exclusion principle. So they follow all the rules of Fermi Dirac statistics. So now let us see how we can apply this Fermi Dirac statistics to a system of free electrons in metals. Now, the particular point that we are going to actually derive, or we are going to find, will be the number of electrons available, or the number of electrons within the energy range E and E plus dE. I will come to it little later, but first let me write down something and we will be discussing. So let me just write down the topic once again. So number of electrons. Now see, I am no more writing number of particles. We are well defined now. We have well defined this particle. Which particle? We are talking about electrons in the free electron system. So free electron gas system. So number of electrons within energy E and E plus dE. Now, generally when I was a student and I had to study this, I was very confused. Why are we finding this energy range in terms of a continuous change? Why not EI in terms of, say, the discrete energy level EI or EM or EK or EJ? Why are we have been talking about energy to be discrete till now. And suddenly, now when we are applying the Fermi Dirac statistics, why are we doing it in terms of a continuous energy change, E and E plus dE? I had this question very much. So, frankly speaking, I did not get the answer very clearly written anywhere. But the particular answer which finally I settled into is Let's see. When I am drawing the energy levels E1, E2, E3, E4 till say this is at E1, E2 and somewhere as EI. These individual levels are no doubt they are discrete. However, think when I come down to a real life situation, the distance between this, I would not say distance, the difference in energies between E1 and E2 or say between E2 and E1, they are in terms of magnitude very less, right? So actually when I look at the situation, when I look at the system from outside, E1, E2, E3, they are as if very close to each other. They are superposing on each other. So we can consider this to be a band, isn't it? So we can consider this E1, E2, E3 and I can consider this to be a band of energy dE. So from a discrete value of energy E1 or another E2, suppose I'm considering a few of the discrete energy levels E1, E2, E3, E4 and I'm clubbing together and considering the entire band of energies and we are calling that as dE. So this is the meaning of this particular line as well. So when I am trying to find out or when I am discussing about an energy band, right? An energy band within lower limit E and higher limit E and E plus dE. This is what I need. It is not like I am changing again the discrete values of energy to a continuous. It is only that we are considering the range of values. So I hope this will help you to understand what we are doing here. So now, from where will I get this number of electrons? From where will I get the number of electrons? This number of electrons, if you remember, there is something called an Ni by Gi, which is the distribution function given for our Fermi Dirac systems, right? So, this Ni by Gi is the clue from where I can also find out these number of particles. Just think with me. When I ask you what is this Ni, this Ni are the number of electrons in the energy level Ei. Correct? Now, instead of asking that what are the number of particles exactly on the energy level Ei, what we are asking what are these numbers within not only Ei but say some energy level E and E plus dE. So instead of having Ni, I am distributing these numbers over a range. And in this case, what will I call this Ne? I will call this Ni as NEDE. Are you all with me? Did you all follow? That when we were writing the distribution function in terms of a discrete energy level, we had Ni by Gi corresponding to the energy level Ei. But when now I am considering an energy range, what will I just do? I will change this Ni discrete value to another range. And where is this range found out? This range is to be found out within the energy range dE. So my numeral now becomes NEDE. Right? In the same format, following the same rule, this Gi also will become GEDE. And if you go back to the pages, if you go back to yesterday's class, we have already found out what is GEDE, or rather first we found out GPDP, then we converted to GEDE. So now, can I not write it as, do I not have this formula? See, from discrete, let us go to this range. So what did I have? I had Ni by Gi is equal to 1 by e to the power Ei minus Ef by Kt plus 1. From this discrete topic or discrete point, now we are going to the range. So what will I now write this as? I will now write it as NEDE by GEDE is equal to 1 by, now see, when I was doing this for the discrete value of EI, I had an EI here. But now where am I? Where I am working with an energy range E and E plus DE. So this e to the power, this particular EI is now the beginning E minus EF by KT plus 1. So this is how our scenario changes. This is how the perspective changes, or we are using the same Fermi Dirac law from the discrete level to the continuous level. From the discrete level to the continuous level. So you all have understood. So now let me get back to this. And today, what are we trying to find out? We are actually trying to find out what is this NEDE? What are the number of electrons within the energy range E and E plus DE? So, what can I write it as NEDE? I can write NEDE as GEDE by this. All I have done is I have taken this GE to the other side, and this gives me the answer of this question. This gives me the answer of this question. Right? So, when we are in this scenario, now let us see. GEDE value we had yesterday only we had derived. But if for simplicity, so that you can understand once again, I will derive this once again, but I will start from GPDP. I will start from GPDP and then I will convert it to GEDE. If I place it over here as it is, I am not going to disturb this part. Remember, yesterday only we had found out the number of states possible or available within the momentum range P and P plus dP, which we were calling it as GPDP. GPDP. And what we had found that out as? Remember, we had found that for fermions, it comes out to be 8 pi V by H cube P square dP. Remember, we have already discussed and we have already very elaborately found how to do this. We have derived this. But what I want, I do not want GPDP. I want GEDE. I do not want the number of states within momentum range P and P plus dP. I want the number of states within the energy E and E plus dE. So what am I going to do now? I am going to convert this GPDP in terms of energy and write it as the GEDE. Fine. But then how is this P and E related to each other? Reminding all of you, E is equal to P square by twice M. Now, yesterday only I had told you that we are writing the total energy as kinetic energy only, because when we talk about free electrons, they are not supposed to be under any potential. So, their potential energy is 0. So, their energy is simply P square by twice M, or can I not write as P square is equal to 2me, right? So if P square is equal to 2me, what is the value of P? The value of P is under root 2me, right? So let us have this as one of our equations. Going back to P square is equal to 2me, what we will now do? We will differentiate this. P square is equal to 2me on both sides. So what will I get? I will get 2p dp is equal to, m is a constant, so it gives me 2m de. Correct? 2 gets cancelled, so I have p dp is equal to mde. So I have the individual value of p as under root 2me, and I also know that the value of p dp is mde. Now, what will I do? I will use this in my GPDP formula. And what is that? GPDP is equal to 8 pi V by H cube P square dP. This is our GPDP formula. And P square dP is nothing but P into PdP. So what will I do now? I will take the value of this individual P as root over 2me and put over here. And I will take the value of PdP as MdE and put over here. So that will be our final answer. So what can I write now? I can write this as, instead of GPdP, now I have GEDE is equal to 8 pi V by H cube. P is root over 2me. PdP is MdE. So that is my value of GEDE. Now let us do little bit of mathematics and see. Let me take this under root over here. So what will I have? I will have GEDE as 8 into root 2 pi V by H cube. Now see, we are having m in two places. This m is coming with an under root m to the power half, and this is m to the power 1. So can I not write it as m to the power 3 by 2? And then I have this e under root, which means e is having a power of half, and I'm left with dE. So that is my last value. This is my final value of the number of states possible in the energy range E and E plus dE, which is our GEDE to be put in this formula. Hello Shomudra. So children, he is actually your senior. He is now in second year. So it's good to see that old students are coming back. So now let us come back to our class. So what we will do now, we will take this value of GE and we will put it over here, and that will give our answer of how many number of electrons is possible within any given energy E and E plus dE. So finally, what can I write? I can understand this formula is looking very horrible, very big, but trust me, if you are able to understand, it is not a problem to write at all. So what is my NEDE? My NEDE is 8 root 2 pi V by H cube M3 half E half dE by e to the power E minus EF by KT plus 1. So that brings us to the final equation of our class today, which means these are the number of electrons possible within the energy range E and E plus dE in a Fermi electron gas. Now, this is how. See, you must be wondering till now that why are we doing statistical mechanics? Where do we actually apply them? This is where you see we have actually applied the Fermi law. We have applied the Fermi Dirac Statistics to a real life system, which means now it is not random that say when I am considering a free electron gas, the electrons will not be distributing themselves as per their will. They will have to follow a rule that if they are within an energy range E and E plus dE, this has to be their number. This has to be the law that they follow. And while we have done this, see once again, in the very beginning we had told that when the system has a large number of particles, we no longer look into an individual particle's movement. That how this one electron will be moving and what will be its equation of motion. Rather, what we do, we consider the entire scenario. We consider all these electrons as a single system, and then we bring in some statistical laws. And exactly that has been done. Instead of worrying about one electron's movement, we have done. We have distributed them over some energy level, and we have applied statistical mechanics to get their number. All right. So this is how generally the application of statistics is done. Statistical mechanics is done. The two examples, this example that we have done today both of them belong to the Fermi Dirac Statistics. Under the same chapter, you also have, remember, Bose-Einstein statistics. And reminding all of you, Bose-Einstein statistics belongs to bosons. And as an example of bosons, I have told you that photons are bosons, right? Now, where else we have come across photons? We have come across photons in black body radiation, remember? So actually, when suppose I start from the distribution function of Bose-Einstein statistics, I will be very easily able to derive the Planck's radiation law. Remember, Planck's radiation law was given to us by Planck on the basis that energy is not continuous, they are acting like particles, they are acting like photons. And he had given us a Planck's radiation law. And it is very easily, we can derive the Planck's radiation law starting from the Bose-Einstein distribution function. So as of now, I am not going to directly show you that over here, but such type of applications are always done, and statistical mechanics is used for real life systems, and the results are derived. Okay, so as I have told you already, that this brings us to the end of statistical mechanics lectures. Let me, before I finish, let me just give you a recap of what all we have done in this chapter. So what are the recaps? I will begin with the macro and micro states. We have studied, we have done how to solve the problems of macro state and micro state, depending on whether the system is distinguishable or indistinguishable. Alright, so that was the first thing we did. Then we studied about the three classifications of statistical mechanics. We divided statistical mechanics into three parts: MD, BE and FD. Then we have discussed about the individual parameters. We have compared each of these three. And from there, today we have done a few applications of the Fermi Dirac statistics. So as of now, this is where you all need to be very prepared with from the point of view of your examinations. For any further inquiry, for any further doubt, we are always available in our group. We will be discussing it over there. So is this fine? So is there any small doubt which I can very easily clarify now, or else we can always go back and we can talk about it. So please give me some feedback that you all have understood. Am I audible? Okay. Okay. So now I can see the things moving. So that's all for today, and that is all for statistical mechanics in our online classes. What we will be doing from the next week? First, we will finish up our Maxwell's equation topic. We are left with that one topic in CO2, and after that we are going to step into our optics classes. Okay, so that's all for today. Have a good day. Okay, good, Shomudro, that you are able to remember. So okay, bye bye children. Have a good day.